Hi, welcome back. So in part 3 we're going to take a look at a couple more algebraic methods. In part 1 we did talk about the algebraic factor cancel, and we had the substitution method. You might remember those. So let's take a look at a couple that where sometimes it's not going to fall under one of those categories. And the first one we're going to take a look at is the conjugate method. Now the conjugate method is very simple to recognize. Typically when you have a radical or a square root involved. In this case we're going to multiply the numerator and denominator by the conjugate. So let's take a look. If I were to try to plug in the 4, remember the first thing you always want to check is substitution. If I plug in the 4, we get the square root of 4, which is 2. 2 minus 2 is 0. Plug in the bottom, we also get 0. So we know right away that this is our indeterminate form. So to solve this one, again, I'm going to rewrite the limit like we did before. But this time I'm going to multiply both top and bottom by the conjugate. So we get the square root of x minus 2, x minus 4, and the conjugate is the square root of x plus 2. We're going to look at the conjugate of the part with the radical part, and that's going to make it easier for us. On the bottom, we get the square root of x plus 2 as well. When you simplify the top, what we wind up with is a difference of squares. So we get this x minus 4 on top. And on bottom, if you notice, we already got that x minus 4 there. So don't distribute the bottom because we know that those are going to cancel out. And indeed, that's what's going to happen there. And we're left with the limit as x approaches 4 of 1 over the square root of x plus 2. And now if I plug in the 4, that of course becomes 2, and we get 1/4. For our final answer right there. Very easy to do. Now, here's a tricky one. Would we use the conjugate for this one? Well, if I plug in the 3, on top I would get 0, but on bottom, notice I would get 6. So the answer is I would not use the conjugate. And that is because this is not indeterminate. Not indeterminate. Matter of fact, what would the answer be? Well, what's 0 divided by 6? That's just 0 right there. So not in every case. Always check substitution first. That's the rule for these. And the last technique we're going to take a look at is the greatest, well, one of the last ones, is the greatest common denominator method. These are your complex fractions. Just 3 words. The AP does not like complex fractions. So we're going to get rid of them by using the greatest common denominator. So if I look here again, if I try to plug in 0, we get 1/2 minus 1/2. So the top again is just 0, and the bottom is 0. So to do this one, we're going to multiply by the greatest common denominator. And to do that, we're going to look at all of the denominators. The 2, the x plus 2, down here there's a 1. And I'm going to multiply that. The G, C, D. The greatest common denominator. You might hear me say GCF method, greatest common factor method. And to get that, all we're going to do is we're going to multiply by everything there. When I say the greatest common denominator, to get the greatest, see, normally we think least common denominator, but we want the greatest because we want to cancel, make sure all the fractions cancel out. And it's easy to do 2x plus 2 times 1. And I'm going to multiply everything by that. Multiply everything by this. And I can do that in my head. So if we multiply everything by that, we would get the limit as x goes to 0. If I multiply the 1/2 by my common denominator, the 2's would cancel, and I'm really just left with this 1 times x plus 2 minus 1. And if I multiply the x plus 2 times my common denominator, the x plus 2's cancel, and that's going to become times 2. Now the bottom, I got to multiply the bottom too. It has that x, but I'm also going to multiply it by the denominator as well. Nothing cancels in this case except for the 1. I mean, if you want to cancel the 1s, you can. And we're left with 2 times x plus 2. And we just simplify. Simplify the numerator. Don't forget to rewrite that limit here. And this becomes x plus 2 minus 2. So the top just becomes x. Don't simplify the bottom. We get x times 2, x plus 2. And if you notice in this case, the x's do cancel. And if I rewrite my limit again, we're left with 1 over 2 times x plus 2. And if you plug in the 0, we get 1/4 right there. Very easy to do. Let's try number 2 here. In this case right here, again, if I plug in the 5, on top I do get 0, and on the bottom we do get 0. So I'm going to multiply by my common denominator, which in this case is going to be x, 5, and that's just the 1 down here, don't worry about that, so it's just 5x. And I'm going to multiply everything by 5x. This becomes, if I distribute here, the 5 times x here, the x's will cancel, we're left with 1 times 5 minus 1 times x. On the bottom, we're going to get the 5x times this x minus 5. Now this one's a little bit trickier, because when we simplify the numerator here, this becomes 5 minus x over 5x times x minus 5. And it doesn't look like anything cancels, but they do. Because 5 minus x is the same as x minus 5, just negative. So I can say that 5 minus x is the opposite of x minus 5. So when these cancel, that just leaves me with a negative 1 on top. I'm left with that negative 1. And on the bottom I have that 5x. And now I can just substitute in. I get negative 1 over 25. Easy peasy. All right. Very easy to do. But now let's take a look at some special limits. These are little kind of wonky ones right here. The first one being the limit of sine of x as x goes to infinity. Well, when we think about this, if we think of sine of x, we can't, if I try to put in sine of infinity, I get nothing. I don't know what that is. But when we think of what the graph looks like of sine of x, it goes like this. It just goes up and down forever. We call this an oscillating function. In other words, it's just going up and down. So we call it an oscillating function. In other words, it's never approaching a number. And therefore, we say these don't approach a value. So what's going to be the answer? Well, we don't write this. But because it's not approaching anything, we just say this is D and E. And we say because sine of x oscillates. And that's going to be our answer right there. Oops, let me fix that. There we go. And that's going to be our answer. So here's another one. What about cosine of 1 over x? Well, this is different now. I'm taking 1 over x. Now, even though cosine oscillates, but the question is, well, what's happening with the inside? We want to know what's happening to the limit as x goes to infinity of 1 over x. Well, if we think about that, if I take a number and I divide it by a really, really, really large number, take 1 and divide it by this number, I can go forever. Well, that's getting really super small, which means it's approaching 0. So when I think about this, this becomes 0. So if I plug in the infinity here, this becomes the cosine of 0, which is 1. And there's our answer. All right, so I hope you enjoyed the videos. Come back and join us for the next ones. See you soon.